Hi there, welcome to this lecture series on matrix algebra. This is lecture 30, part 1. The topic is quadratic forms. In this lecture, we'll cover various topics related to quadratic forms and connecting it to symmetric matrices. Also, we will look at diagonalization by a variable change, and then we'll also look at curves defined by a quadratic form in 2 and 3 variables. Let's get started. So first, a definition on quadratic forms. A quadratic form in the variable x, where x is a vector containing elements x1, x2 to xn. It is in a homogeneous polynomial of degree 2. So what do we mean? We mean that each term is a polynomial of degree 2, meaning the degree of the polynomials in each variable xi appearing in that term, if there are multiple of them, they all add up to be 2, and there are no other terms. We can take an example. Let's say P of x contains 2 entries, x1 and x2. Let's say we'll have x1 squared plus 4x2 squared minus 8x1, x2. And this is a quadratic form because we can verify it by looking at each term and check that. So the first term is only x1 to the power 2. So this is totally power 2. So that's degree 2. And the second one is x2 to the power 2. So that term is also degree 2. And the third term is basically x1 times x2, meaning x1 to the power 1 and x2 to the power 1. And then 1 plus 1 is 2, so the degree of this term is 2. Okay, so another example, this function q of x, depending on x1, x2, and x3, takes this form. There are 4 terms, and we can verify that each term is of degree 2. So the first term, x1 squared, degree 2. Second term, x2 squared, degree 2. And the third one, x3 squared, degree 2. And the last term, x1 times x3. So this is degree 1, and that's degree 1. And 1 plus 1 is 2, so that's a term of degree 2. And then we can throw in some examples that are not quadratic form. For example, this f of x, which is x1 squared plus x2 squared plus 3 times x1. So it has 3 terms. Let's look at the first one. It is quadratic, and the second one is also quadratic. And then the third term basically is x1, meaning is x1 to the power 1. So this is not of degree 2. This is a term of degree 1. Therefore, this is not in quadratic form. And then gx, let's say if you have terms that is not in a polynomial form, and it's some other function of any of the variables x1, x2, x3, and that will make it not a quadratic form. We now seek connections between a quadratic form and matrices. So we seek a matrix representation of a quadratic form. So let's see, given an n by n matrix A with elements aij, we now consider the following quadratic form. Q of x is x transpose times A times x. If we write out elements, x transpose is now a row vector containing all the x's. A is the matrix, and x is the column vector. And if we work out these 3 products, and then you see that the q of x equals to the summation of all possible quadratic terms. So it will be the summation over all ij running from 1 to n of aij times xi times xj. So a sum of all these terms where aij is a constant number and x1 has power, xi has power 1, xj has power 1, so this term has power 2. So this summation here, we can be more specific. It is actually a double sum. You can sum either in I first or in j first. It doesn't matter. So summing I from 1 to n, and then summing j from 1 to n. Okay, so we see that an expression, a computation like this, x transpose times a times x, that gives us a quadratic form. Conversely, actually every quadratic form can also be represented as this matrix product with vectors for some suitable A matrix. Let's take some examples. So we have two matrices. One is A and the other is B. They are chosen like this. Now let's first compute the quadratic form with A. So x transpose times A times x. If we write out, it's the product of these three, a vector, a matrix, and a vector. And if you work out all the terms, the two multiplication, you will get this expression, x1 squared plus 3x1 x2 plus 5x2 squared. So here in particular, the term 3x1 x2 actually comes from two terms in the product. One is the product 3 with x1 x2, and the other is 0 with x1 and x2, and you add them up and you get 3x1 x2. Similarly, we can compute the x transpose times b times x. Putting in the numbers for the B matrix, we get that, and you work out and you get this quadratic form, where the red term 3x1 x2 is obtained actually by this term -1 and this term 4. They will both be multiplying with x1 and x2, so you add them up and you get 3. So here we make an important observation. We see that the quadratic form ended up here, they are the same. So xt ax equal to xt bx. So we have the same quadratic form, and yet the matrix A and B, they are not the same. So each quadratic form, if you want to write it as something like this in the matrix form, there are infinitely many matrices you can put in there that will give you this quadratic form. So we are interested in a unique way of finding a quadratic form and connecting it to matrices. That is, if we put the restriction that the matrix shall be a symmetric matrix, and then we have the following theorem. So every quadratic form can be uniquely written as Qx is x transpose times A times x for some symmetric matrix A. So let's take some example. So if I have a quadratic form like this, x1 squared plus 3x1 x2 plus 5x2 squared, and then I can write it as x transpose times A times x uniquely for a symmetric matrix A. A would be on the diagonal is 1 and 5, which comes from the coefficient in front of this term and that term, and it's symmetric, so this term would equal to that term, and then they also must add up to be this number 3, so it's a 3/2 and 3/2, and there is a unique way of determining this matrix A. Let's take another example with 3 variables, x1, x2, and x3. I have a quadratic form like that, and I wanted to write it in the form x transpose times b times x, where the b is a symmetric matrix. So the B will be a 3×3 matrix, and it's uniquely determined the following way. So first, the diagonal terms is 1, -5, 0, which comes from 1 in front of that. -5 will be in front of x2 squared, and then the x3 squared, which is 0, which doesn't appear here, will be the last one. And then take this term x1 times x2, and then you divide it by 2, and then you get 3 over 2, 3 over 2. They will be the element b12 and b21. And then this term here, 8, in front of x2 times x3, you would divide it by 2, and then you get 4, and that will be for the element b23 and b32 here. And then the last one, x1 times x3 is not here, so it's 0. So we put our 0 here. And that's the unique way of determining the matrix B. So there are many nice properties if one has a symmetric matrix. So let's recall a theorem regarding the diagonalization of a symmetric matrix. So it says, we have seen this already in this class, that is, let A be a square matrix n by n and symmetric with real entries. Then, regarding the eigenvalues and the eigenvectors, we have the following. All the eigenvalues lambda r are real numbers. And then, second, we can always find an orthonormal basis of linearly independent eigenvectors. Let's call them v1, v2 to vn. And then we can use these eigenvectors to form a matrix P, which is the column vectors will be just v1, v2 to vn. And then this matrix is invertible and it's orthogonal, and then the transpose of the matrix P is the inverse of the matrix. And then one can diagonalize A by multiplying it on the left by P inverse and on the right by P, and this gives you a diagonal matrix where the elements on the diagonals are the corresponding eigenvalues. We can now put this knowledge into our study of a quadratic form and see what that implies. Namely, we want to see how to diagonalize a quadratic form. So we have shown already that every quadratic form in the variable x1, x2 to xn can be written as the form here, that is x transpose times a matrix A times x, where A is a unique symmetric n by n matrix. Now let's find the eigenvalue and the eigenvectors of A and then use them to form this matrix P, which is an orthogonal matrix, such that I will diagonalize A with this. So P inverse A times P will be D, is diagonal. Okay, so with all that, now we can introduce a new variable, a vector. Let's call it y, which is just a collection of y1, y2 to yn. And it's introduced in the following way, that x is p times y. So meaning y is x, p inverse times x. And then we can write x transpose would be y transpose times p transpose. And then y would be p inverse times x. And then p inverse is just p transpose times x. So using all this, we can redefine the quadratic form in the variable y. So q, originally defined as x transpose times a times x, now can be written as follows. X transpose can be written as this, and we put here, and then x will be put in p times y here. And then we see that in the middle we have p transpose times a times p, which is the same as p inverse times a times p, which is the diagonal matrix D. So this equals y transpose times D times y, where the D is a diagonal matrix. So in these new variables y, the quadratic forms become much simpler. That is, you will only have terms coming from the diagonal, meaning you will only have the terms that is yi square, and they are multiplied by lambda I, the corresponding diagonal terms in the D. Okay, so now the new quadratic form q of y would simply be lambda 1 y1 square plus lambda 2 y2 square all the way to lambda n times yn square. Now this is the end of part 1 of this lecture, and in part 2 we'll look at more examples, and we'll look at the surface and the shape formed by quadratic forms in 2 and 3D space. Okay, so I hope you enjoyed this one, and I'll see you in a bit.